I've been replaying Pokémon Mystery Dungeon Rescue Team DX, my favourite A-button mashing simulator. This one can even play itself. I still love the striking visuals with the sketch shadows. You might be getting deja vu, and yes, I have talked about this game before, but I've evolved since 2020. This time, I'm going to create those shadows, and our journey is going to cover shadow maps, screen space shadows, post-processing, the normal and depth textures, and triplanar mapping. I'll be doing everything in Unity 2022 URP, and here's the shader I came up with. Let's take a quick look at the game in action. When you're in a dungeon, it looks like the scenery shader receives shadows from Pokémon moving through the dungeon, and those shadows act like a mask for the sketch texture. There appears to be a hard line between sketch and no sketch which matches the shadowed areas. Nice and simple. Near your rescue base, and in town however, the sketches overshoot the shadows a bit. At first, I thought the shadows around these trees were baked, but the trees do actually move slightly in the wind. Our shader needs to dynamically generate the sketches, but still be able to overshoot the shadowed region. That means I'll need to find a way to extend the shadows across surfaces slightly before I can use them as a mask. There's a surprising amount of work that goes into just extending the shadows, and I'm sure you can find a simpler solution, but I think I came up with a fun way of doing things that touches a lot of different bits of Unity. Let's start by cracking open the frame debugger and seeing how URP renders a frame. This little gizmo breaks down how each draw call is issued to your GPU and gives you lots of useful information such as the textures, matrices, variables and keywords used for this draw call, what the output looks like, and even why the GPU couldn't batch two draw calls together. If you're getting thousands of draw calls and you have no clue where they're coming from, the frame debugger is your friend. Going down the list, we start by clearing a texture called Main Light Shadow Map Texture, and then we draw the main light shadows to that texture. That sounds like it might be helpful for us. This shadow map texture contains the distance of the closest objects the directional light sees when it looks down at the scene, and we can use it later when drawing objects to the screen for realsies to check whether a given pixel is in shadow. Later in the rendering loop, you'll see the Draw Opaque Objects group of draw calls, which draws objects to the screen, and we can verify that these draw calls read from the main light shadow map texture, which implies we might be able to read this texture ourselves. We can go one step further. I'm going to use post-processing to apply my sketches, so it would be useful to have access to a shadow map relative to the screen. We can do just that by adding the Screen Space Shadows renderer feature to URP. Don't know what this does under the hood, as far as I'm concerned, it's magic. In the frame debugger, we can see that this feature runs after mainlight shadow, and it reads from mainlight shadow map texture and writes to a new screen space shadow map texture. Then, if we check a draw call within Draw Opaque Objects, it now reads from screen space shadow map texture. Nice. Let's finally boot up a code editor and start putting together a post-process effect. The full source code is available on GitHub, link in the description. So is the test scene, minus Mudkip. I don't want to get nuked by Nintendo's ninja lawyers. This post-process will take the screen space shadow map and blur it a little to make it cover a larger area, then we'll use that as a mask for applying the sketch texture. I covered URP post-processing in a previous video about Gaussian blur. Oh, that's useful. But anyway, to recap, we use renderer features to inject a custom path somewhere into URP's rendering loop. There are 4 parts to such an effect. A settings file, which contains all the shader variables we want to tweak using the inspector, a render pass, which manages sending data to the GPU and running the shader, a renderer feature, which creates the pass and injects it into the URP render loop, and finally, a shader file, which defines how we want to mangle the screen pixels. Let's start with the Sketch Settings C# class. This class needs to extend from Volume component and iPostProcess component, which makes our effect compatible with URP's volume system, the same one used by the out-of-the-box effects. The system.serializable attribute is crucial for saving any values we change, and the volume component menu attribute defines the name we see in the menu when we add this effect to a volume. The settings class is largely just a container for the shader variables we want to tweak, and we can list them here by using different parameter types. These are wrappers around basic types like floats and textures. Here's the full list of supported parameters. We're gonna need variables for the sketch texture itself, which looks something like this, a tint color, a tiling amount for the texture, a pair of thresholds to define a fall-off region for the edges of the sketches, an option to apply the sketches twice in a cross-hatched pattern, and a few settings for the blurring that I'll explore later. We also need to provide an isActive method, which lets us run the effect only when the parameters are set to sensible values. We'll say the sketch texture mustn't be null. The isTile-compatible method is probably something to do with tile rendering, but 1 year on from my last video, it's still marked as obsolete from Unity 2023 onwards, which is now called Unity 6, so I still don't really care, and I still just return false, and it still hasn't broken anything, so we Gucci. That's all for the sketch settings file. The second file is called sketch.cs. This class extends scriptable renderer feature, which means it needs to include create, add render passes, and dispose methods. And it'll also contain the whole sketch render pass class. The renderer feature itself is pretty bare bones. It just contains an instance of the pass, which it creates in create, revolutionary, I know, and then injects it into the URP render loop and add render passes if there's a valid, active pass attached to a volume. Otherwise, we save on resources by not processing the pass at all. Dispose will just call a helper method I'm going to define in sketch render pass. Speaking of which, let's write the pass now. It extends scriptable render pass and overrides the configure and execute methods, plus a few convenience methods, namely create material and dispose. The constructor sets up a profiling sampler, which gives us a way to accurately profile the effect, and then we can set where to inject this pass into the rendering loop. There are many places we can choose, but I settled on before rendering post-processing, which might be a misleading name since we are doing post-processing, but the before refers to URP's internal post-processing, things like bloom, vignetting, and color adjustments, which are included out of the box. The create material helper method I wrote tries to find the shader file and creates a material instance, throwing up an error if the file is missing. Pretty simple. And then the configure method is for setting up resources required for the pass. The class has 4 member variables, the material, which we just dealt with, and 3 render textures. That's a lot, but they're all crucial. Configure runs once when the pass is created. Inside it, I'm pretty sure reset target sets all of the behind the scenes resources back to a blank slate. Then we use reallocate if needed to set up the first texture, named temp text handle. Okay, there's lots going on here. The RT handle type is a wrapper around the old render texture type, which is meant to work better with URP. We're going to copy the screen contents to temp text handle for reasons I'll explore later, so it uses the same render texture descriptor as the camera texture, with a couple of tweaks. Next, we set up 2 more RT handles, which I've named Shadow Map Handle 1 and 2. The shadow map only uses the red color channel because it's grayscale and uses a precision of 8 bits. So we use the R8 texture format to save on texture memory over the camera texture, which apparently needs the RGB 111110 float format. Reallocate if needed is meant to scale your textures automatically if you resize the screen, so that's nice. We're going to need depth and normals textures later, so we will configure both of those here too. Now let's execute some frames. This is the juicy, meaty bit where we start telling Unity to draw some stuff. First, stop running immediately if this is running on a preview camera. You know, the little preview window that pops up when you select the camera. Otherwise, oh baby, yeah, it breaks. Next, let's make sure the material exists and then start to set up a command buffer. As the name suggests, this is the list of GPU commands which will be executed in order. We'll grab the sketch settings values from our volume and pass most of them directly to the shader via the set methods on the material, with a couple of tweaks. First, we'll send over not only the blur amount, which is the size of the blur kernel, but also an extra spread property, which is the blur amount divided by 6. That's the standard deviation used in the Gaussian value calculations. My previous blur video goes into more detail about that. Second, we'll convert the cross-hatching boolean to a float value that's 0 or 1, because even though HLSL supports bool types, the material doesn't. Now it's time for some texture foo. Let's open up a profiling scope and then do a bunch of blit operations. That means copying one texture to another, optionally applying a shader pass while doing so. we can find the screen space shadow map texture using its internal ID, and then grab camera's output so far into a variable called camera target handle. When we execute the command buffer, whatever data ends up inside camera target handle is going to get plastered onto the screen. Using the frame debugger, we can see that the texture looks something like this directly before we run the post-process. Then, let's copy the shadow map into one of the RT handles, the one named shadow map handle 1, using the blip method. I'm going to go off on a bit of a side rant here. When you do this blip between shadow map texture and shadow map handle 1, the compiler will complain. Uh-oh. Yeah, so this is one of my gripes with URP's post-processing APIs, where we have the old render texture APIs and the new RT handle-based ecosystem, which clash a lot. You're meant to use the new Blitter API, but there didn't seem to be a way to get this texture copy working unless they used the old, deprecated blip method, because a lot of this tends to be poorly documented. However, it looks as though the effect works, and that's good enough for me. Just be prepared for this to all break in some future Unity version. Now it's time to run the blur shader, which of course we haven't written yet. The shader will contain 3 passes. The first is for applying the sketch pattern using a blurred shadow map, and the other 2 contain horizontal and vertical blur passes respectively. We use a 2-pass blur because its computational complexity increases linearly with image size, whereas a single-pass blur increases quadratically. 2-pass is vastly more efficient. I have also included an extra blur step size parameter, which is an optimization I devised since my Gaussian blur video. Essentially, we can skip out some pixels from the blur kernel, so we end up with a sparse kernel which still operates on faraway pixels, but with gaps to increase efficiency. The reduction in the number of calculations is quite drastic for large blur kernels, and many times the difference is imperceptible. We'll only run the blur if the kernel size is strictly greater than double the step size, and then to do the blur, we play some ping pong. That's the process of blitting from one texture to another and then back again, often performing different shader passes during each blit. The first blit from shadow map handle 1 to 2 will run the horizontal pass, which has an index of 1 because it's the second pass in the file, and like all good programmers, we're using zero-base indexing. Then we'll blur from 2 to 1 with the vertical pass with index 2. Here, we're using the new Blitter API, which Unity intends you to use from now on. We can then attach the fully blurred texture to the material under the name shadow map texture, which will make it available for use in the sketch pass. And finally, we can run the sketch pass. We can't blur from camera target handle to itself, so we'll go for another game of ping pong and copy camera target handle to temp text handle without using material, and then back again, this time specifying the 0th shader pass. Fun fact, ping pong used to be called whiff waff. No wonder so many people celebrate independence from the British. After closing the profiling scope, we can execute the command buffer and release it back to the command buffer pool. All that's left is the dispose method, which releases the memory used by the 3 RT handles. We're all done on the C# scripting side, and all that's left is the shader file. First, there's a shader lab wrapper around everything, with associated boilerplate. Inside that, I'll have an HLSL include block containing everything that's needed by multiple passes. No point in declaring stuff twice. Then, I will have the sketch pass, the horizontal blur pass, and the vertical blur pass in that order. HLSL include will contain some include files from Unity's shader APIs, notably the declare depth texture file, which sets up the camera depth texture and associated helper functions, and the blit file, which sets up a blit texture variable containing the source texture whenever we use one of these shader passes in a C# blit operation. It also gives us a pre-written vertex shader for rendering a full screen quad, so we can focus entirely on writing the fragment shader, which is where the wizardry happens in post-processing. I'll also pack in a few blur-related variables we passed from sketch settings, a Gaussian function, and then wrap up the HLSL include block with a helper function for sampling the depth texture. Let's write the horizontal blur pass, the second pass in the file. I explored this in the Gaussian blur video, but briefly it's generating a Gaussian kernel and multiplying the contribution from nearby pixels. This time it's also factoring in the blur step size for an efficiency boost. I've also made one other change. Let's see what happens if we run a regular blur on the shadow map and apply the sketches. The sketches nicely extend past the shadowed areas, which is great, but they also extend past object boundaries. which is not so great. I ended up fixing this by calculating the depth of the center pixel, the distance from the camera, and then I compare it with the depth of the kernel pixels and only consider them as part of the blur calculations if there's a small depth difference. Otherwise, I assume I'm checking past an object boundary and ignore them. The vertical pass is very similar to the horizontal pass, except I'm blurring along the y-axis instead of the x. That leaves the sketch paths. This one needs access to the normals texture, which we can get with the declare normals texture include file, plus the remaining shader variables and sketch settings, which I will list here. I'm also going to define a triplanar sampling function based on cat-like coding's implementation. Thanks, Jasper. I decided triplanar mapping would be a good way to apply the sketch texture. Since we don't have access to mesh UVs because we're doing a post-process, I'll need to use other information. Applying the sketches in screen space doesn't look great, so instead I can derive the world coordinates of each pixel using the information in the depth texture, then use triplanar sampling to sample that sketch texture 3 times using the XY, YZ, and ZX planes of the world position as 3 sets of UV coordinates, and then choose the sample which most closely corresponds to the direction of the pixel's normal vector faces. That's why we needed the normals texture too. If we're cross-hatching, then I'll rotate 90 degrees and do a second triplanar sample. Sure, doing this many samples for each pixel is excessive, and you can probably optimize out these matrix multiplications, but I'll leave that as homework if you want a more efficient shader. Finally, let's grab the shadows from Shadow Map texture. If you recall, we sent the blurred shadow map result via this texture, and use Smooth Step to blend the edge regions of the shadows using the thresholds we defined in sketch settings, and use the resulting value as a mask for applying the sketches. Phew, that was a lot of code, but here we are. A slightly fancy way of applying the sketches the way Mr. Pokémon, John Pokémon himself, intended. To recap, we learned about shadow maps, screen space shadow mapping, the frame debugger, renderer features, the new Blitzer API, the normals and depth textures, and triplanar mapping to create this effect. And as I said, probably an overcomplicated way of doing all of this, but I wanted to do this in a fun way that also gave me an excuse to explore lots of different Unity features all in one effect. I'm happy with the result, and it has decent performance, even with large blur kernels. Thanks to my Patreon supporters and everyone who watches my tutorials. Your support means a lot to me. If you want to support me and the channel, Patreon is a great way to do that, but you can also check out my premium asset packs such as Retro Shaders Pro or Snapshot Shaders Pro. I try and pack them with as many features as possible to give you the best possible value for money, and it's always cool seeing what people make with them, so I'd love it if you could check them out. Links in the description. Until next time, have fun making shaders.